Okay. Here we go. Inserting into a linked structure. So we know the idea of a linked structure. We have nodes, and in the nodes we have reference to some data, and we also have reference to some successor node. That could be null, but it could also be another node, kind of like this, where this light blue one here has some data in it that we don't really care about at this point, but its successor is this green, and then this one's successor is this turquoise color, and then this one's successor is the black box. So if we ever wanted to add something to the front, so let's say we're looking at this link structure right here, yellow, gray, black. But I want the blue one to now be at the front. If this was an array, I would have to move the black one down, the gray one down, the yellow one down to make room for the blue one. And so I can make the blue one go in front in index 0 of my array. But this isn't an array. This is a linked structure. So if I want to add something in front, I could have a billion things in my linked structure. But if I want to insert something to the front, all I have to do is say, okay, hey, new node, your next is what head points to. What head is a reference to, the yellow one. So we set the new node's next to yellow, which was the old head. And then we just need to say, okay, and then the head of the list, well, the head of the list is now the blue one. So boom, have the head of the list reference the blue one. Now, the order of nodes is blue, yellow, gray, black. We've inserted it into the front of our structure. That's fantastic. Adding to the middle is a little bit more complex. It's a little bit more complex. It's not scary or anything, but there's a little bit more bookkeeping involved. So let's say I want to insert the blue box before the black box. So between the bluish, green, teal, turquoise, whatever, and the black one. I want to put it in between there. So how am I going to do that? Well, what I'm going to have to do first is locate the node that we want the new node to come after. In that case, it's this green one. Whatever color, turquoise, teal, let's call it turquoise. I'm locating the node where the new one will come after. So this one right here, the teal one. Alternatively, you can think like the node that comes before the node you're putting it in front of. That doesn't help. That makes it worse. I want to find, if I want it to be inserted between this one here, this teal and black, I got to find teal. And an easy way to do that is just loop through, right? Like let's say this has the number 0, 7, 10, 15, and I want to add this blue node that has the number 12, and I want it to be in order. So I could be like, okay, well, I'll have reference to this one and be like, well, what's its number? Is it less than or greater than? Oh, okay, move it, until we find where it goes. So we need to get our hands on this teal node. But then once we do, I'll have some reference. I mean, you can call it whatever you want. Here I call it current. Maybe it's not a great name, but current. It's a reference to the teal one. But we have to be very careful on... The process here is the same as before. Wait, let me make sure I'm recording. I am recording. The process is the same as like inserting into the front. We got to update what nodes as nexts are referring to. But order is really important here, because think for a second. I'm going to copy this. Paint. If you consider, if I show up and say, okay, current, don't reference black anymore. You reference the new node, right? Now, what do I need to set this new node to be referencing, right? What does that need to reference? Well, it should be the black box here. But the problem is that black box, we have no reference to it anymore. And if we can never get access to this thing anymore, it's gone. I mean, a solution is to have like another thing called like after, if you want, which is just a variable that points. So you have current, and then after, you know, it kind of points at the two there. So you could say, okay, well, blue one, your next is equal to what after is pointing to. Or an even simpler solution is, okay, new node, your next is equal to current's next. So current's next is, oh, it's the reference to the black one. So we say that. Then we can say, hey, current, teal, your next, it's not this black one anymore. It's the new node. Now we're safe. So before, if I tried to update current's next first, I might lose access to this, which is bad. So that's why we want to make sure we're updating the new node's next first in this particular scenario. So, I mean, here it is drawn out with these pictures. Set the new node's next to what the current's next is, and then set current's next to the new node. There we go. And then adding to the end. So we saw that adding to the middle is like it's a more general case, right? If we have a list of 1 billion things in it, you can only ever add to the, like adding to the front is a special case. Where adding to the middle is just wherever. It's wherever. So it's much more general because it might be between the 0 and, like, you know, the first and the second thing, or the second and the third thing, and so on. We're adding to the front. That's the special case. If we go back here, we can think of adding to the end. So let's say, here, I'm gonna get fancy here. I'm gonna take this. Nice. So let's say I want to add to the end. And what I'm gonna do is I'm gonna show you that adding to the end is actually exactly the same process as adding to the middle. So by default, our nodes, if their next is not referencing some other node, it references null. So here's the process. Say, okay, new node, your next is current's next. Oh, okay, so I'll just reference null, which is that stand-in value for nothing. Then, hey, current, your next, you're not going to point here anymore. You're going to point to the new node. It's the exact same process. New node points to current's next. Current's next now points to the new node. So adding to the middle and adding to the end is actually the same algorithm. Where adding to the front was the slightly different one because we didn't need to go look for some current or anything. It was just there. Man, we're missing like 21 people in class today. That's no good. Hopefully this improves because, all right. Whoops, we want this. I hear a boop. It's because, oh, you mean they're skipping because they know this stuff, or you're here because you're the best? Is that what you mean? I can't. No, you're the elite ones. They are not. Oh, okay, I understand. Okay, adding to the end. Now removing. Okay, removing from the front is definitely going to be the easiest one. All you have to do is say, okay, head, if this is the thing we want to remove, okay, the teal one in this case, all I have to do is say, okay, head, you're not equal to teal anymore. You're equal to head's next. So I say, hey, head, what's your next? Oh, that's this yellow one right here. Here, copy. Let me draw it again. So I say, okay, head, what's your next? Well, head's next. Oh, well, that's this one right here. Okay, so that's really, it's the reference to that. So head, you're actually equal to head's next. Oh, okay, so I'm just gonna go, and you go here now. Huzzah. Now nothing has reference to this. Garbage collector comes along, doesn't exist anymore, and now look, yellow is the new head. So yeah, that one's gonna be the easy one. You're going to, what are you doing? Oh, I guess, wow, I really appreciate your commitment to this. It's very good. That is intense, well done. Deleting from the middle is maybe one of the more complex ones. But again, it's still relative. Like, it's still simple, but it's a little bit more complex, definitely more complex than deleting from the front. So deleting from the middle, we need to have, like, let's say we are deleting this teal one. So I need to somehow get reference to the node right in front, the previous. Because then I need to just say previous, okay, your next is current's next. That's the process, right? So say previous, your next is what current's next is. So you just update that to point to that. This suddenly disappears and we're good to go. But you may be asking the question, how do I get the previous? Uh-oh, look, there's a bug in this picture. See, this one has a dark square around this one, but this one does not. Uh-oh. How did I do that? There's a GitHub issue someone can make and fix if you want. So you might be asking, okay, if I have current, if current is the node I want to delete, how can I get access to the previous? Because because Dr. Hughes made a huge stink about putting, like, you can never get a predecessor node. You can only ever say, hey, current, what's your next? I'm not allowed to say, current, get your previous. So how on earth do I get reference to this? That's a question. Someone needs, so think about this for a second. How can I, if I have reference to current, how can I get current's previous? Come on, someone's got to have an idea. And it's not a trick question. It's just like, you're going to hear the answer and go like, oh yeah, okay, fine. Loop through until current's next. Exactly. That's it. So I have current. What we do is we just start here. Let's take copy. Paste. Okay, and then we'll cut this because we don't care about this right now. So all I do is I say, okay, head, are you the thing I want to delete? No. Okay, so we're not deleting from the front. So I get something to reference this and say, okay, hey, this node, is your next the thing I want to delete? So hey, is your next, which is this, current? If it is, well, we found the previous. If not, carry on. Okay, so don't go here anymore. Boom. Now we are referencing this and we say, hey, yellow, what's your next? Oh, well, that's this blue one. Is that current? No. All right, carry on. Go to the next one. Okay, blue, what's your next? Is that current? Yeah. Oh, okay, I guess, okay, we found it. Good. Now I have previous and current, so I'm good to go. So although you can't directly get a previous, you can ultimately get a node's predecessor, assuming it has one, like it's not the head. You can get any node's predecessor by doing a linear search starting at the beginning. So now here's one of the downsides of this singly linked structure. Okay, we see that inserting and deleting is easy. All I have to do is update a couple of things. If it's an array, I might have to shuffle around bajillions of elements. That's computationally expensive. Where with these lists, all I have to do is just update a couple pointers. It's constant time work. But the downside is, if I'm at current in some array, where current is some arbitrary index, and I want current's predecessor, all I have to do is say, okay, I minus 1, I'm there. Where if this is a link structure with a billion nodes in front of current, I got to do a linear search to get the current. So now we have a downside to this link structure. There's no free lunch. There's always pros and cons to these things. So that's kind of a, shucks situation. Does this take n time? The looping to find the predecessor? Yes, if that's what the question is. Yeah, okay, cool. You're absolutely right. It is linear time. Well done. Deleting from the end. Okay, note. Okay, this is an important note I want to emphasize here. Head is not a node. Okay? It's a reference to a node. For example, head equals some node and head.setNext some node have two very different meanings. Let me draw what these mean. This is really important to make sure you understand the difference. Head is just a reference to a node. So if I have here, I'm gonna get all fancy. I'm gonna make this courier because it looks like code. Head equals some node. And then over here we have head dot head set next to some node. Okay. So here is the difference. I have some reference variable head. And it references something. I don't care what it references. It's referencing something. Maybe it's null. Maybe it's the head of some gigantic list. I don't know. But I've got some variable head. That's a reference to some nodes. No, it's a reference to a node. That's the idea. Now, I also have... Nope. Let me draw the box. Some node that is a node. So this circle is my node. Here. Okay. I'm going to copy this because I'm going to be able to use it. And you know what, for simplicity, I'm actually going to add, let's pretend head is referencing some node. Okay, there, now I'll copy. Okay, oh, and I'm also, shoot, I'm missing this. All right, cool, here we go, this is fantastic. I'm hearing boops. Let's make sure everything's okay. Can head be referenced by something else? Head of a head? Well, head is just a reference value. Can head be referenced by something else? You gotta have a million aliases to the head node. I have a question because all the nodes are different colors. Why don't we just use something like head color, but have to use net? What? The colors in my picture are irrelevant. Don't go look for meaning where there's no meaning. Okay, so here is what head equals some node is. We come along and we say, oh, okay, well, head, you used to point to this, but copy the contents of some node. What's the contents of some node? Well, it's a reference to this blue node. So make head a reference to that blue node. That's what head equals some node does. Okay? Can a link array and node hold? You guys are asking all of these questions that are not related to what I'm showing you right now. Let's focus on one thing at a time. Okay. Now, head.setNext to some node is entirely different. When I come along here and I say head, oh, okay, that's, you know, it's a reference to this node. Set your next. Oh, so now I'm saying to the node itself, set your next to what? Well, what's the contents of some node? Well, copy over the reference. That's a reference to the blue one. So it does this. So head equals something is updating what head's referencing. Head.setNext updates what head's referencing's next is. Two very different things. Because Head is not a node. Head is a reference to a node. Okay, let's see all of these questions. Okay. Head is the starting point, yeah. Can head be referenced by something else? Well, it's just a reference variable, right? So you could have 1,000 variables called like head 1, head 2, head 3, head 4, all pointing to the same start of a link structure. If you're asking, oh, can you have a reference to the reference variable? No, that's not a thing. Head of a head? Yeah, that's not, because head isn't a node. It's just a variable, right? Remember, nodes are objects. Variables are just a value that like, and it's a reference variable to that node object. Okay, we're gonna ignore the color. Don't the colors represent variables? No. Here I'm just drawing. What? I'm just making the note here difference. The colors are arbitrary. It's just to make it obvious that, you know, they're different things. But because all the nodes are different color, why don't we just use something like head color, but have to use next? Yeah, I don't really understand that question. Can a link array end node hold a reference to another link array head? What's a link array? Help me out with what you mean by link array. A node can hold reference to anything. Does head mean anything but the start, like a head? Does head mean anything but the start? I mean, the name of the variable is arbitrary. We could call it, this is totally not the head of a link structure, and have it be referencing the head of a link structure. It's just a variable name. But T2, yeah. Can a node hold a list? Yeah, a node can hold a list. A node's data could be a node. A node's data could be a node that references a node that references a stack of nodes. Whatever we want. It's crazy. We can do whatever we want here, as long as we're following the rules. But I'm El Jimador. I'm not sure what you mean about the link array. Okay, the link structure. Can the link structure end node hold a reference to another link structure head? Well, yes, because if I have here, let me get one of these pictures. Copy image, and there. This is head 1, this is head 2, okay? This points to null, I'll just do that as like a dot, this points to null. These are two separate lists, right? One has a head variable reference called like head 1, and it's a reference to the beginning of this list. This is the linked structure, right? And this is a separate linked structure. This doesn't really have anything to do with it other than getting us to the beginning of it. It's just a reference variable. Oh. And so what I could do is at the very end, I can be like, hey, head 1, you're next, 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 next. Set your next to head 2. Oh, okay. So, boom, there. Now we just concatenated two link structures together. Boom. It's one big long link structure. Sure, we have some value or some variable here, head 2, that references some node in the middle. I mean, so we don't really care about this anymore. But yeah, we could totally do that. Here, I'm gonna draw that in a different color, purple. So now we go there. There, cool. Could totally do that. What? This shouldn't be too bad. This is if you're I can guarantee you, if you are struggling with the idea of a node, you are trying so hard to understand something that's not there. All it is a series of nodes that reference some other node, that reference another node, that can reference another node. I can tell from a lot of the questions I'm getting that a lot of you are trying to connect dots and make relationships that don't exist. That you're trying to make it more complicated than it is. Stop doing that. Classic beginner programmer mistake. What we want to do, it's just a thing with a thing. Really, that's it. It's an object that has two fields. One field is a reference to an object of the same type, and the other is a reference to some arbitrary value of type t, right? Because it's generic. But I can tell because people are asking about colors, where colors don't really mean anything here. And people were saying, oh, can you have something referencing a reference variable? No, because that's not a thing that we've ever done. And stop trying to make it a thing. Don't make it a thing. Keep it simple. Keep it simple. Remember, if you want to be a computer scientist, you got to think stupid. We are not capable of making things hard for ourselves. We got to keep it simple. Do we have any questions about the nodes though? Because ask. And when I'm saying like, oh, if you're not understanding the node, I'm not saying if you're not understanding the node, you're stupid. I am not saying that at all. I'm saying you're working too hard. You're trying to be far too smart. You're not being stupid enough if you're having a difficult time with this. Am I wrong to think it's sort of similar to how Python handled lists and pointers to lists? That's exactly what it is, right? How you can say like append to the list. Are you thinking of like when you say like append my list? Do you remember that? How like in Python, if I had, in fact, it's even more interesting. If you're remembering, like when I said to Python, hey, here's my list called head. If I go to the end and I say, hey, append to the last node here, append to head, which is this whole thing, head. Oh, okay, well, what does head reference? Well, it references the first node. So now, cyan is followed by yellow, which is followed by gray, which is followed by blue, which is followed by black, which is followed by cyan, which is teal, yellow, gray, blue, black, teal, yellow, gray, blue, black, teal. This will go on forever because it's got a loop. It's a cycle. It can loop on itself. That's like what we did in Python. We could do the exact same thing here. It's not like, oh, is this like the thing in Python? No, it's literally the exact same thing. The only difference was in Python, when we said list, it meant the whole thing. Where here we're saying head is a reference to the beginning only, but I could go to the end of this linked structure and say, hey, your next is a head. And, oh, okay, so I copy over what head is, which is just the reference to this teal one. So we add that reference to the teal one. So you're right, Bilbo. It is exactly that. Infinite loop. You could, yeah. And you know what? Let's do that. Okay, I'll have head. Okay. A node of type okay. I'm gonna have some fun here. Equals a new node where what? I just said it cannot be node of type node cannot be applied to character. Do I have to make it exist and then set the, maybe I never set the constructor. Okay, head dot data is f, right? Well, let's see what happens. Because you remember like Google Colab would stop with recursion. Okay. So I'm going to test you. And I want you to watch what I'm doing. And then I'm going to print out, I'm going to put this in a loop and print out the contents. And I want you to, based on what I'm writing here, you are entirely capable. I believe in you. You are capable of telling me what we'll see printed out. Set data to head dot set next to A, and then A set next to A. Okay, so I am now going to say character equals head. So I'm going to create a node reference variable called current that's going to start by referencing what head references. So the beginning, the node that has the value f in it. So while, here, I'll get rid of this last line here for a sec. While current is not, current, yeah, is not equal to null. So if current's not null, print out current dot get data. Then current is now equal to current dot get next. So I'll take, if current's not null, I'll print out current's data, which in this case should be f, right? And then I'm going to say current is equal to current's get next. So when I ask current, hey, what's your next? Well, that'll be pointing to A, right? Because head's next is A. Okay, great. So this is a reference variable to A. So now current references the thing that comes after current. We just move it down one. So, okay, it's now referenced that. Current is referencing the node with the value u in there. So it is not null. We print out the u. Current equals current get next. Well, A's next by default is null. So when we go back up to the loop, current is null. So when I hit print on this, what do we expect to see printed out? An F and a U. That's all. Yeah, there you go. Exactly. That was nice. Now, it's going to get nicer, because I am putting this line back in. With this change, what's going to happen? This one line I put in here, what's going to happen? I'll give you a second to think about it. Run. So I stopped it because this would be an infinite loop. In fact, we couldn't even see where it starts. It's not even showing you. I'm gonna rerun it, but then stop it much quicker. Okay, cool, stop. No, still wasn't fast enough. Maybe there was clear. Was I quick enough this time? Ah, there we go. So this time I hit run. We see the F, then the U, because this is what I did. I had where's the circle? Head, and then the thing referenced by A. So then I had, okay, this was head. I'll just draw it as an H. And it contained the F, right? And this was the variable A, which referenced this, and that contained the U, right? Then, let's go back to the code. Head, F, A, U. We said head, set your next to A. So head, your next now is what A is. Great. So originally, I said, okay, current starts at this, print it out. Current, get your next. Well, that's the U, so you don't point here anymore. You point there. Print out the U, great. You don't point there anymore. You point to null. We finished. But now, when I went in and added this line where A, set your next to A, well, what did that do? Well, we took, okay, well, your next is what A references, which is itself. So now it was, okay, current, you start at F, print out the F. Current, what's your next? Well, it's this one with the U. Okay, so update current to be current, get next, print out the U, and then current, get your next. Well, its next is itself, and then print it out. And then get your next, and then get your next, and then get your next. Long story short, it is never possible to have current being equal to null now because A, which is at the end, just loops back on itself. There's no way to get out of there. We're stuck. So that's why we can do that. Look, if you're thinking, whoa, he's trying to trick us. No. The rules are we have a node object that has data and we can set next to, and the next is another node. Which other node? Whatever node we want. It just set any node we want. The less exciting than I had hoped. Iteration won't break it. For any infinite loop? No. Well, yeah. No, you can't, actually. In fact, you asked a really interesting question. Recursion, when we had the infinite loops with recursion before, we'll get an exception. But that's a consequence of how our computers, like, physically and logically work. Where an iterative, just like a loop without recursion, it won't cause the same issue. Which we will learn about this later in the course. But it's a very interesting idea. But a loop like this? No. It's just like me saying while true. This will run forever until the power goes out, you know? Cool. Okay, the linked structures. And that was that. Here was the code. Okay, variations. So remember, like I said, oh, okay, well, your nodes only point to the next. You might say to yourself, why? Why not have a node where it has 3 values? Data, next, and previous. All right, yeah, sure, why not? You could totally do that, where every node knows its successor, but also knows its predecessor. Totally. Of course, when you go and do your adds and your removes, there's more bookkeeping to deal with because you got to make sure to upload that one's previous and then this one's next and that one's next and that one's you know. There's more bookkeeping involved, but you absolutely could do it this way. There's nothing stopping. Can you run a loop on time, not a counter? There would be a way, but you'd still be using a counter. Or you could, I guess you could look for a time difference where you get the system time and then look for a delta to be greater than a certain amount of time. Yeah, you could do that. But how would you know that your loop's actually done calculating what you want it to calculate? What if it needed like 1 more second? Okay, so yeah, there we go, cool. All right, so we finished talking about the link structure. And the link structure was not an abstract data type. The link structure was more analogous to an array than anything else. We built a stack with an array, right? So we have a stack with an array. The contents of the array stack, okay, we had that array that had reference to the things that were on the stack, and the top of the stack was always the node, like at the end of the array, not at the beginning, at the other end. And, pardon me, and we might have to expand capacity every once in a while, but whatever. Now, let me ask you. We have a stack interface. If I click this, we will get to this. It'll download this file. What does it mean to be a stack? We can push, we can pop, we can peek, is empty, and size. That's all we need to be a stack. Then we went along and we implemented array stack, where we said, okay, this is how you push, this is how you pop, peek, size, and is empty. And we had 2-string because we always like to have good 2 strings. So we had our array stack. But if these link structures are analogous to arrays, can we use a link structure to implement a stack? Can we make, instead of an array stack, can we make a linked stack? And the answer to that question is absolutely we can. All we have to do is write push pop peak size is empty. Okay? The interface doesn't tell us how. Our implementation does. So we are going to implement a stack with the linked container. So we'll keep track of the top with some field called top that, like, remember how with our array, we always had it so the end of the array was the top. And the reason we liked that was because anytime you pushed and popped from the array stack, it would always just grow from the one side. Where if you always had it such that index 0 was the top, we're gonna run into like a lot of extra work, because if we push something, we gotta move everything down the array. And if there's a billion things, if there are n things in that array, we gotta move all n down to add a new one. And then if we pop something, we gotta move all n things back. So there's a lot of extra work there. If we made index 0, the thing at the beginning, the top. So that's why it was the other end. Computationally, way easier. There's nothing stopping us from implementing a stack like that. We totally could. It's just, if you were given the choice to use which, like one or the other, you're gonna want the one where the top is the other end of the stack, because it's gonna be way more computationally efficient, because there's way less shuffling around. The linked stack, on the other hand, we don't need to have the top be like at the other end. We can have the top be the front of our linked structure, like the head. Because remember how easy it is to add and remove things from the front of a stack? And if I'm at the top, add and remove things from the front of a linked structure. If I'm at the top of a stack, I always just care about the successors. I don't have any predecessors, so what I'll do is I'll just have some reference variable, top, and some counter variable, count, to keep track of how many things we have. Top is basically the head of this linked structure here. Okay, this dot here means null, okay? So if I want to come along and push this light baby blue block on here, okay, I increment count, but then all I have to do is, let me go back here. All I have to do, if I'm doing that, all I have to do is adding to the front. This is the process. Take the new node, set your new nodes next to the head, and then have head reference the new node. So putting that in the context of our stack words, cyan, baby blue, your next is what top reference is. Oh, well, that's this node right here. And then top, you now reference the baby blue. Boom. That's all it is. That's all we gotta do. There's a little bit of overhead in there, in the idea of like, well, we have to create the node, update, set the nexts and whatnot as well, because the blocks aren't nodes. The blocks are the data in the nodes we care about. But that's what we're inserting into the front, is that node. So we just throw this in a node and insert in the front. And then if we want to pop something, it's just, if I scroll down here, adding to the, deleting from the front, just top, your next is, or top, set yourself to your nodes next. Basically, hey top, I know you point to green right now, but ask the green one, hey, what's your next? Oh, well, it's this one. Okay, great. Top, now reference this one. Boom. The green one's gone. Cool. And we just update count. So now we can come along and implement our stack with a link structure instead of an array. What's really cool about this is they're both stacks, and we can guarantee that because we're gonna have both versions of our stack implement the stack interface. If we are writing a class that correctly implements a stack, then it's a stack. No ifs, ands, or buts, it's a stack. Java guarantees that, because if you don't, remember if I go here and say, if I don't write, let's say I didn't write push. It's gonna, like, I can't run this because it's saying error, you didn't implement the stack interface. You're missing push, right? So I can now start writing a linked stack that implements a stack. And if I do everything correctly, I'll have a stack. But the way it works under the hood is entirely different than the array stack. But they're both stacks. It's just one was built that way and the other was built this way, which is pretty cool. And then this is where computer scientists really love to start geeking out. We love to go like, well, okay, so we have two different implementations here. Just like we talked about the array stack, I could implement the array stack where top is at index 0, but that's a terrible idea because we know we rationalize through why it makes more sense for top to be at the other end of the array. So we were able to compare those two implementation ideas and very quickly throw away the terrible one. But now we have array stack and linked stack. They're both stacks. Which one's better? Well, this is where we like to geek out. This is where we like to say like, okay, let's see if we can conclude. How can we measure better here? So really quickly before we go, to pop, you just said, well, let's learn. So here's where we'll start. Implement the stack. Top, it's a node with something of type T, because notice that this is a stack of type T, and then size. Our constructor, top is null, size is 0. We push, okay, create a new node with the element we want to push, and then say to push, set your next to whatever top is. It might be null, might not be, and then top is the thing we just added. This is inserting to the front, increment size. Pop peak, get the data that we're going to return. Top is now top's next. Decrease size, return element. And then we have that catch if we run out of space. And then size in is empty, or just that. We're going to revisit this on Tuesday in lecture. Like we'll go through this code a little bit more detail, but look how simple this is. There's no need for expand capacity anymore, right? There's nothing crazy. Just create a new node with the element that we want to push and then insert to the front of a link structure. Pop, remove from the front of the link structure. That's all. Okay, in case comparing speeds, do you just try them both in different scenarios? Or do you worry about removing the pop node? We're going to get into measuring computational complexity pretty soon. Link stack. The next topic, topic 9, algorithm analysis. So this is where we'll actually get into comparing what's better, which is really fun. That's really cool. But we are well over time, so that's that. Any last questions before we retire for the day and for the rest of the week? And I guess the whole week next week? Here, I'll just stop recording.